Welcome back to the channel, guys. Thank you for liking, thank you for subscribing, right? Remember to share the video with a friend so that they can share it with a friend to have them subscribe as well, right? That's how we're going to build the channel. Now, today what we're going to look at is the trigonometric identities. And to just get right into it, I'm just going to use a right triangle right in this little corner just to identify the trigonometric ratios. So recall that if you have a right triangle like this, 90 degrees, we know that the longest side of the right triangle is the hypotenuse, which is abbreviated as HYP. Let's use a different color for that. Right? And if we're looking at any one of these angles in relation to the angle, let's say this is angle alpha, right? This side would be the opposite of angle alpha, so we abbreviate that OPP. And this side would be the adjacent side, abbreviated ADJ. Now, the sine, cosine, and tangent of alpha is in relation to the opposite, the hypotenuse, and the adjacent side. So recall that the sine of alpha would be equal to the opposite, that's OPP, over the hypotenuse, HYP. The cosine of alpha is equal to the adjacent side over the hypotenuse. And the tangent of alpha is equal to the opposite side over the adjacent side. All right? And we're just taking it from the foundation so that you can see the relation with these ratios and the unit circle that we're about to draw right here. So we're just going to get an axis. I hope I draw this a little bit accurate. Let's go like that and like that. I'm going to just get the unit circle like that. It doesn't have to be all the way on the axis. We could have drawn a nice little circle here, but doesn't really matter. So we're going to consider this a unit circle, not drawn to scale, right? And remember, the radius of a unit circle is 1. So it's from the center, the origin, touching on the point on the circumference. And we're going to complete a right triangle by taking a perpendicular line from that point all the way down onto the x-axis. So right here would be a 90-degree angle, right? And we're going to call this angle right here, we're going to call that alpha just the same, right? So notice that on the unit circle, right, when you're going in the x direction, right, we talk about the cosine of the angle, and we're going in the y direction, we talk about the sine of the angle. Why is that? Recall that the radius here is 1, right? This is the opposite side, and this is the adjacent side, right? So let's say we name this OPP and we name this ADJ in relation to the angle alpha. Now we know from the trigonometric ratio that the sine, let's remove this little piece right here. From the trigonometric ratio, we know that the sine of alpha is equal to the opposite side over the hypotenuse. What's the opposite side? We're going to leave that as OPP over the hypotenuse, which is 1, right? Right? So in reality, the sine of alpha is just equal to the opposite side. So therefore, we can replace OPP here with just the sine of alpha. So we can put the sine of alpha right here, or sine of theta, or sine of A, or sine of any variable or any unknown you want to use for the angle right here to represent that angle, it's fine. But for now, we're just using alpha. Now, the cosine of alpha, that's the cosine of alpha, is equal to the adjacent side over the hypotenuse also. So if you take the adjacent side, ADJ, over 1, that's just equal to the adjacent side. So the cosine of the angle is equal to this distance right here. So we can replace ADJ, that's the adjacent side, and I'm always going to be writing and erasing so you see where it's coming from. This is just equal to the cosine of alpha. So the cosine of alpha always goes in the x direction, and the sine of alpha always goes in the y direction. And that's how it is for the entire unit circle, right? If you're going in the x direction, it's cosine of the angle, and if you're going in the y direction, it's sine of the angle, right? Now, what we're interested in is to get the basic trigonometric identities from this unit circle right here with an inscribed right triangle, sorry. So we also want to know what the tangent of alpha is, right? And the tangent of alpha is equal to the opposite side over the adjacent side. So that's the opposite side over the adjacent side. So that's OPP over ADJ. But we already have this variation over this side. So what we're going to do is replace OPP with the sine of alpha. We're going to replace that with the sine of alpha. And we're going to replace the adjacent side because the adjacent side is equal to the cosine of alpha. Right? And we just got that identity for the tangent of alpha, which is in relation to sine and cosine. So it's the sine of alpha over the cosine of alpha. We could also note that if we're using basic coordinates, you know, a coordinate is in the form x, comma y, right? Let's go back to basic. So if you're going in the x direction, that's horizontally, and in the y direction, that's vertically, right? So it means that the sine of the angle is also equal to y, and the cosine of the angle is also equal to x. And you may see that in some books, or it may be explained that way. So we could replace all of this, right? We don't have to use OPP and ADJ because we're on the unit circle. We could use its coordinates. So the sine of alpha is in the y direction, and the cosine of alpha is in the x direction. And this still holds because the tangent of alpha will just be y over x, right? Now that we know these basic functions, we're going to look at the reciprocal of these functions, right? Because that's all that there are, the reciprocal of these functions. The reciprocal of these functions, we can list them as the cosecant of alpha. We can list the reciprocal of cosine of alpha would be secant of alpha. And the reciprocal of tangent of alpha is the cotangent of alpha, right? And if you recall what reciprocal is, right, we're just taking the flip. So this would just be 1 over y, right? But we know that y is equal to the sine of alpha. So the cosecant of alpha is 1 over the sine of alpha. And the secant of alpha is equal to 1 over the cosine of alpha, because it's 1 over x, right? It's the reciprocal of this. And x is equal to the cosine of alpha. So that's the cosine of alpha. And then, of course, the tangent of alpha will be the reciprocal of the cotangent, I should say, would be the reciprocal of the tangent of alpha. So cotangent of alpha is equal to the cosine of alpha over the sine of alpha. That's the reciprocal. Or the cotangent of alpha is equal to 1 over the tangent of alpha, right? So whichever way works, just the same, depending on what identity you need, right? So these are the 6 basic trigonometric functions, right? And as you can see, all of them are in relation to the 2 most basic ones, sine and cosine, right? Once you know sine and cosine, you can know everything else, right? So these are the basic trigonometric function. But there's also a nice little property, I would say, that we could also manipulate these formulas to get what the square of cosecant of alpha is, the square of secant of alpha, and the square of cotangent of alpha, right? So We're going to look at that when we get to the Pythagorean identities. We're going to show that if we just square both sides, right, what happens really, right? Now, we're going to move into the Pythagorean identity before we get to the others, right? Because we already have the unit circle set up right here for us. Now, for the Pythagorean identity, recall that the Pythagoras' theorem says that a squared plus b squared is equal to c squared, right? Where in this case, c represents the hypotenuse, right? And if you look at our right triangle, the hypotenuse here is 1. So we're gonna do that. The hypotenuse here is 1. So that's 1 squared is equal to A and B can be any one of these two sides. Doesn't matter which one you choose, A or B to be, right? So we could say let A be equal to the cosine of alpha. So we have the cosine of alpha all squared plus the sine of alpha all squared, right? And we can rewrite this as 1 squared is just 1. Cosine alpha squared can be rewritten as cosine with the squared on the inside of alpha. Just like that. You can write it in that notation as well. Sine squared alpha. All right? And that is how we get to the Pythagorean identity, right? And we could have taken it from here because we know that if this side is x and this side is y, then x squared plus y squared is equal to 1 squared. And 1 squared is just 1. And what we have here is the equation of a circle centered at the origin, right? And we're just replacing x and y with sine of alpha and cosine of alpha, just the same. It will get us to the Pythagorean identity. But there's something interesting about the Pythagorean identity, right? We could get two other identities from this, or even more, but two main ones that's also used, where if we divide through by the cosine squared of alpha and the sine squared of alpha, we can get two new identity. And we're going to do that. We're going to do that in this space right here. I'm just going to erase this piece. I'm going to erase this piece right here. And we are going to take the fact that the sine, let's close this. We're going to take that the fact that the sine squared of alpha plus the cosine squared of alpha is equal to 1. And again, this is what we're going to do. We're going to divide first through by sine squared of alpha. So if we divide through by sine squared of alpha on both sides, right? If we divide through by sine squared of alpha, look what happens. Sine squared of alpha divided by sine squared of alpha just gives me 1 plus the cosine squared of alpha divided by the sine squared of alpha. Recall that the cotangent of alpha is equal to the cosine of alpha over the sine of alpha. And if we just square both sides, we're going to have the cotangent squared of alpha is equal to cosine squared of alpha over sine squared of alpha, right? So we could replace this entire quotient right here with the cotangent squared of alpha equal. Now recall that 1 over the sine squared of alpha, right, is the same as the cosecant squared of alpha. Because why that is, the cosecant squared of alpha is equal to 1 over the sine squared of alpha, right? We just squared both sides based on the previous identity that we showed from the unit circle. So squaring both sides gets us to this, and we're just going to replace this with the cosecant squared of alpha, right? So now, if you look at what we have here, is another Pythagorean identity where if we transpose to remove cotangent squared of theta on that side, you get the cotangent squared of theta, well, cosecant squared of theta minus the cotangent squared of theta is equal to 1. And that's just by dividing through by the sine squared of theta. Now, if we divide through by the cosine squared of theta, let's do that. So I'm going to leave that there for a bit, and we're going to remove these pieces. Because if we now divide by the cosine squared of theta, of alpha, sorry, the cosine squared of alpha, cosine squared of alpha. Look what happens. The sine of alpha over the cosine of alpha is the tangent of alpha. So therefore, the sine squared of alpha over the cosine squared of alpha must give us the tangent squared of alpha. It's a nice little identity that we had previously also. The cosine squared of alpha over the cosine squared of alpha, that just simplifies to 1. And all of this is equal to 1 over the cosine squared of alpha, which is the secant squared of alpha. Because again, the secant of alpha is equal to 1 over the cosine of alpha. Right? So this is another identity taken from the Pythagorean identity here. So another Pythagorean identities. So these are the three main ones that they always show. These ones that I box in right here. So that one, this one, and this one. And they're all coming from the fact that the equation of the unit circle is x squared plus y squared equal to 1. And that's centered at the origin, right? Now, we're going to move ahead and we're going to look at some other identities. Now, before we look at these identities, I want to prove to you why these identities are true, right? So, to do that, I'm going to need all this space right here, right? The first one we're going to be looking at, the sum and differences identities, right? So we're gonna move all of these spaces out.